The valence bond theory has some limitations because it doesn't agree with the shapes of the molecules that we see that we were just talking about in chapter 7. So let's take a look at water. So we have an oxygen atom with 1s2, 2s2, 2p4. The electrons that are unpaired and are ready to overlap with the hydrogen are in the 2p orbitals, and there's two different ones. There's two different p orbitals that these electrons belong to. So let's try to draw two different p orbitals. So this one I've drawn in blue, and this other one I've drawn in green. The one that's already full that we don't have to worry about, that's the one that's going into and out of the screen. So I picked that one to not worry about because it's hard to draw. So I was trying to make it easier on myself. So now we have the hydrogen. We're going to have this over here be an s orbital. So there's two different hydrogens. Let's draw one over here and one over here, overlapping with the green p orbital and the other overlapping with the blue p orbital. So if this were true, if this were really happening, the angle between these two hydrogen atoms would be 90 degrees because this p orbital is on the y-axis and this is on the x-axis, and they would be 90 degrees. And that is not what we see for a water molecule, so we need to modify the theory to make it agree with the shapes. That's where the thought of hybridization comes in. Mathematically, you can combine the wave functions to make different orbitals. So these are hybrid orbitals. The hybrid orbitals are not different orbitals for the atoms. They are just a change that takes place when we're trying to bond the atoms together into molecules, because these molecules have a different shape than what the atomic orbitals would suggest. We make these hybrid orbitals by combining the atomic orbitals, again mathematically, and the number that you have is going to be equal to the numbers that you combined. So if you combined three orbitals, if you use three orbitals to produce the set, then the set that you produce is going to also have three orbitals in it. And the set of hybrid orbitals are all equivalent. So they're equivalent in energy and they're equivalent in shape. So that gives these symmetrical shapes that we have been looking at in the previous chapter, chapter 7. Since we are using this theory to explain the shapes that we learned about in chapter 7, then there is complete agreement between these hybridizations and the shapes that we've already learned about, because the hybridization that we're talking about was meant to explain these shapes. So of course it agrees with the shapes that it's trying to explain. And these hybrid orbitals are the ones that are going to be used to form the first bond in a molecule. So they are going to be forming sigma bonds. The pi bonds that we mentioned are only formed by the unhybridized orbitals that are being left over. So let's check our understanding, especially of point number 3, by combining an s orbital. So we're going to combine an s orbital that happens to be the 3s, an s in period 3, and we're going to combine that with two p orbitals. So we have an s, a p, and a p. So that's 1, 2, 3 that we're combining. So we are going to get a set of 3 hybrid orbitals. And the name of these hybrid orbitals is based on what is combining. So since we're combining an s and 2p, these would be the sp2 hybrid or hybridized orbitals. Some of these hybridizations kind of just make sense visually. If you combine something with a sphere like an s and only one of the p orbitals, which already has kind of an 180-degree shape, then what happens is that we get two equivalent sp orbitals, kind of one sticking out on each side of the atom. So here I've put them together. I've drawn one in green, one in blue, and so they end up forming this 180-degree separation. So this is the kind of hybridization that takes place in a linear molecule. So in a linear molecule, you have two electron regions that you need to make room for. So you're going to combine two atomic orbitals and end up with two hybridized orbitals to hold those two groups. And they end up being 180 degrees apart. If you have three electron regions, you need to combine three atomic orbitals in order to get these three hybridized orbitals. And when you draw them, when you superimpose these on top of each other, it looks like this. And these large lobes are being spaced 120 degrees apart, the trigonal planar shape that we are already familiar with. Once we get into 3 dimensions, they're a lot harder to draw. So I would definitely recommend you looking at drawings in the textbook. But I would like to point out that the number that you're combining, again, 1 and 3, are going to give the number that you end up with. You end up with 4. So when you combine an S and 3 P's, you're going to get 4 hybrid orbitals, and the name of these is based on what was combined to make it. It's called sp3. This is all the S and the P that we have. So for the shapes that are for 5 electron regions and for 6 electron regions, have to include some D. So for 5, we need an S, we need 3P, and then we need a D. And so that would make 5 orbitals to take care of those 5 electron regions. Then when you have to accommodate 6 regions, we need an additional D. So we need the S, the 3P, and 2 of the D. And those 6 resulting hybrid orbitals are called sp3d2. Again, just talking about what went into making the hybridized orbitals. So I've copied this from your textbook because I thought these drawings were better than what I could do. These are ones that we've seen before. We've already seen that the 2 electron regions will give a linear molecule with 180 degrees. 3 regions will give that trigonal planar geometry with 120 degrees. 4 will give the tetrahedral with the 109.5 degrees. 5 will give trigonal bipyramidal geometry with some 120 degree separation and some 90 degree, depending on whether the groups are equatorial or axial. And then the 6 regions make this octahedral shape where everything is 90 degrees. So the only thing new on this chart is this additional column, which tells the hybridization that went into making this shape. So to make these 2 hybrid orbitals, you need an S and a P. These are called sp hybridized orbitals. The set of 3 is called sp2 hybridized. These 4 orbitals are sp3 hybridized. And then the 5 are sp3d hybridized, and the 6 are sp3d2 hybridized. So this is the additional information that we're learning in this chapter. It does match what we've learned in the last chapter. It matches the shapes because the whole reason behind the hybridization theory was to explain the shapes. So, it makes sense that it matches. So when we were trying to figure out the hybridization, just go ahead and do what you did before to draw a Lewis structure and figure out how many regions it has so that you can figure out the electron geometry of the molecule. And once you've figured out that electron geometry, then just go ahead and choose the hybridization that agrees with that geometry. And both the geometry and the hybridization are based on the number of electron regions that you have. So these are the order of the orbitals, first the S, then the 3 P's, then the D's. And however many regions you have, that's how many orbitals you're going to need. So if you have 3 regions, you can just choose 1, 2, 3, and you know that it's going to be an sp2 hybridized. If you have 5 regions, you choose 1, 2, 3, 4, 5, and you know that it's going to be sp3d hybridized. So that is helpful as well. It is interesting to note that some molecules don't need this hybridization theory to explain their shape. We mentioned before that if water did not have any hybridization, it would hold the hydrogens at 90 degrees. Instead, it's kind of based on that tetrahedral shape with the 109.5 degrees, but the lone pairs squeeze the hydrogen slightly closer together. So water itself is actually 104.5 degrees separation. When you go down to sulfur, the next atom down below oxygen on the periodic table, this is a lot closer to 90 than it is to 109.5. And then when you go one more row down on the periodic table to tellurium, you actually do get something that is 90. So dihydrogen sulfide and dihydrogen tellurium do not need hybridization to explain their shapes as much as water does. Let's go ahead and draw the Lewis structure of carbon dioxide and take a look at each of the atoms and how they might be hybridized. So in this carbon dioxide molecule, the carbon has two regions of electron density. It has two bonded atoms and 0 lone pairs, so that makes two regions. So remember, if you need two regions, we're going to use an S and a P to form hybrid orbitals. So this carbon is undergoing sp hybridization, and that's what lets it hold these two regions in a linear shape. The groups are 180 degrees apart. The oxygens in this molecule are both the same. They both have three regions. Each oxygen has a bonded atom and two lone pairs, so those are the three regions. So we need to use 1, 2, 3 orbitals to hybridize together to make a set of 3 hybridized orbitals. So those would be called sp2 hybridized orbitals, and that is the set that gives us the trigonal planar shape with 120 degrees separation. So these two lone pairs are being held at 120 degree angle away from the bonded carbon. So it might be more accurate if we tried to draw these two lone pairs as sort of a trigonal planar shape with the 120 degree separation.